All right, indeterminate forms with L'Hopital's rule. I'm sorry, I clapped in that little thing right there. All right, last year we did L'Hopital's rule, and we applied it when we got an indeterminate form of 0 over 0. Remember? And so when we get an indeterminate form of 0 over 0, we take the derivative of the numerator, derivative of the denominator, and we evaluate. All right. We still are supposed to kind of take derivatives of the numerator and denominator separately, but I might not show that all the time on these notes. Right? However, on the AP exam, we need to do that. So in our first example, if I have the limit as x approaches 0 of e to the 2x minus 1 over x, we try to substitute in, but what happened? I get 0 over 0. And so what needs to actually say is I'm supposed to take a limit as x approaches 0 of e to the 2x minus 1, and that is equal to 0. I take a limit as x approaches 0 of x, and that is equal to 0, and then we throw out L'Hopital. And so then when we L'Hopital it, we now have the limit as x approaches 0 of what? What is the derivative of my numerator? 2e to the 2x, and then over 1. And now when I substitute in 0, what do I get? I get 2. All right. However, the only indeterminate form is not 0 over 0. We're going to have lots and lots of indeterminate forms, and we're going to talk about those today. All right. We're moving. So again, we do the numerator and denominator separately. That is actually what you should be showing. All right, let's talk about these. So this indeterminate form is going to be infinity over infinity. And I want to talk about speeds of functions first. Do you remember who's the slowest?
Constant.
Okay, constants are slow. Then what?
Constant multiplier.
Then what? Logs. Then what? Polynomials. Then what? Exponentials, like e to the x, 2 to the x, 10 to the x. Then what we're going to actually get to in the next chapter is we're going to have factorials, and then we're going to have x to the x or n to the n's. All right. However, last year we kind of stopped at knowing these, and then this year, next chapter, we're going to get into those. All right. So knowing the speeds of a functions can be really beneficial when we deal with these. All right, so if we look at this first one, we have a limit as x approaches infinity of natural log x over x. If you understand speeds, these are pretty quick. Who wins?
Bottom.
The bottom wins. All right, and so the bottom grows faster than the top. All right, they both go to infinity, so technically these are L'Hopital's rule. However, if we know the speeds, we end up bottom wins, we get what?
0.
We get 0. And the same thing on this next one. I have a limit as x approaches negative infinity of x squared over e to the negative x. If I were to substitute in negative x or negative infinity, technically I have infinity up top and I have infinity on the bottom. All right. However, if you understand speeds, we can do this really quickly. Who wins? The bottom wins. All right. An exponential is going to beat out a polynomial. And so we end up with 0. All right, so this one, I have tangent of 3x over sine of 2x. Again, what do we try to do first? Substitute in. Guess what we get? We get 0 over 0. Technically, should we take a limit of the top, limit of the bottom? Yes. However, for sake of time, we're going to L'Hopital this stuff. So now we have limit as x approaches 0 of what? What's in my numerator now? 3 secant squared of 3x, and then over 2 cosine of 2x. All right, and when I substitute in 0, what is the secant of 0? It's still 1. I square 1, it's still what? 1. So in my numerator, I get what? 3. And in my denominator, I end up getting 2. All right, let's do the next one. I have a limit as x approaches negative 2 of x cubed plus 8 over x plus 2. When I first taught you this in pre-calc and at the beginning of Calc AB. You need to do the sum and difference of cubes. However, now that we know L'Hopital, we can go pretty quickly. All right, so what we substitute in, what happens? 0 over 0. Okay, if this is free response, you got to do the numerator and denominator separately, but let's straight go to L'Hopital. So now I have a limit as x approaches -2 of what? 3x squared over 1. And so now when I substitute in -2, I end up with 12. All right, that was Nick. All right, so this next one I have a limit as x approaches 1 of e to the x minus e to the x over x squared minus 1. So again, what do I try to do? Substitute in. What happened? We get 0 over 0. So now we L'Hopital it. So now we end up with a limit as x approaches 1 of what? E, and then minus e to the x over 2x. Now, if I substitute in 1, what happens?
0 over 2.
Good. All right. So I get 0 over 2. Now, so what do I get? I get 0. All right. Is that a L'Hopital? Even we got a numerator to be 0, but my denominator was not 0, so that one was 0. All right. Make sure you check both. All right. Pretty good. All right. I'm going to move on from that one. I'm going to get into some BC stuff. All right, here we go. Let's look now. So now I have a limit as x approaches infinity of e to the negative x square root x. Again, if you can understand powers, this one's pretty quick. All right, what is this e to the negative x thing? This is 1 over e to the x. So if I were to rewrite this problem, I now have a limit as x approaches infinity of what? Who's up top? Square root x. Who's on the bottom? E to the x. And now if I actually look at the speeds, I have my numerator is a what? Polynomial. My denominator is an exponential. All right. And so who wins? The exponential. The denominator wins. So what does it go to? It goes to 0. All right. And you have to understand the speeds of that. All right, they're a very famous problem now, very famous. All right, write this one out. I have a limit as x approaches infinity of the quantity 1 plus 1 over x to the power of x. You will see this one again. All right. All right. So if I were to substitute infinity here, this one's a pretty nifty problem. All right, if I were to substitute infinity, I have 1 over infinity right here, yes? What is 1 over infinity? 0, right? And then I raise it to a power of, so I have 1 plus 0, basically, to the power of what? Infinity. 1 to the power of infinity should be what? 1. All right? 1 times 1 times 1 should be 1 the whole time. However, this is not. And so what we need to do is we need to L'Hopital it. I am going to set this equal to a thing called y. Okay, I'm just going to set it equal to y. And so how do I get this exponent down? Natural log it, exactly. So now I end up natural logging both sides. So now I have natural log of y is equal to my limit as x approaches infinity of, when I natural log this side, the x comes out front. Okay, remember it's that power property thing? And so now I have natural log of the quantity 1 plus 1 over x. Well, if I substitute in infinity now, I kind of have a natural log of one thing, right? And natural log of one thing is 0, but then we have infinity times 0, and that's also in determinate form. So guess what we do? We're going to L'Hopital. But we can't L'Hopital yet because do we have a fraction at anywhere? No. So we need to change this up a little bit. So I need to get this thing in the denominator, basically. So we're going to multiply by 1 over x over 1 over x. And so now I manipulated it a little bit. So now I have this natural log of 1 plus 1 over x over 1 over x. Do we see how that worked there? All right, so now I am ready to L'Hopital. Here we go. So what is the derivative of this natural log thing?
1 over 1 plus 1 over x.
Okay, so now I have a limit as x approaches infinity. What do we do with this 1 over 1 plus x thing? We throw it to the basement. Does everybody agree with that? Then what can we never forget? Say the chain rule. All right, so then what pops out? What is the derivative of 1 over x?
Negative 1.
-1 over x squared. All right, and then I have it over the derivative of 1 over x, which is what? -1 over x squared. All right, and so now we have to simplify this up a little bit. All right, this is still equal to natural. So now these cancel out. So the -1 over x squareds, when I divide by that, it's really multiplying by like -x squared. And so this part and this part kind of cancel out to what?
-1.
To just 1.
Yeah.
And so now I end up having natural log y is equal to my limit as x approaches infinity of 1 over 1 plus 1 over x. All right. And so now I can actually evaluate this limit. So when I substitute infinity in, 1 over infinity is actually what? 0. So now I have 1 over 1, which is 1. So then I have natural log of y is equal to 1. I haven't solved for anything yet. So how do I solve for y? I exponentiate both sides. So if I exponentiate both sides, I get y is equal to e. And so this is actually one of the many definitions of e. So the limit as x approaches infinity of 1 plus 1 over x raised to the power of x is actually e. Now I'm going to teach you a little trick. If that number right there is anything but 1, that is the exponent of e. All right, and so if this right here is a 2, guess what the answer would be? E squared. If that answer is a 3, or that number is a 3, guess what it is? It'd be e cubed. All right, pretty nifty. All right, cool. We will see that. All right, so this next one we have a limit as x approaches 0 from the right of sine x to the power of x. First try. All right. All right. So again, if it's to the power of, we need to use our new BC rule pretty much. All right. And so how do we get that power down? We need to natural log both sides. And so I set this thing equal to what I call y, and then we natural log both sides. So now we have the natural log of y is equal to this limit as x approaches 0 from the right. And then what comes out? This is the whole reason behind why we do it. X, and then what? Natural log of sine x. Okay, so this is the new part to this year. All right, and so then I need to have a fraction in order to L'Hopital. So what do I need to do? How do I manipulate this? Multiply by 1 over x over 1 over x. All right, and so then we end up having the limit as x approaches 0 from the right of natural log of sine x over 1 over x. All right, let's L'Hopital this thing. So what's the derivative of natural log sine? Cosine over sine, good. So cosine pops up, sine stays in the denominator. Everybody agree? And then it's over, what's the derivative of the denominator? -1 over x squared. As my limit as x approaches 0 from the right. All right, so I personally would use some trig going on here. What is cosine over sine? What is it? It's cotangent, right? And so I have cotangent up top. And then what else do I have going on? What is this -1 over x squared that's really multiplying by what? -x squared. And so then I end up having like a -x squared and then times cotangent x. So everybody see how that kind of worked? All right. And then I still have it equal to natural log y. All right. But if I substitute in 0 right now, what's cotangent of 0? Undefined. And so this isn't good either. And so what do I really want to do with this one? I'm going to L'Hopital this thing again. However, if I have cotangent up top, what do I have on the bottom? So then this is the same thing as saying negative x squared over tangent x. But when I substitute in, what do I actually get? I get 0 in the numerator, and I also get what? 0 in the denominator. So what rule are we allowed to use now? L'Hopital. All right. We are allowed to L'hospital. All right. And so now we're going to L'Hopital it. So what's my derivative in my numerator? Negative 2x. Over, what is the derivative in my denominator? Secant squared. So now I have a limit as x approaches 0 from the right that is still set equal to natural log y. So now when we substitute in 0, what do we get? We get 0 over what? 1, which is what? 0. But my answer is not 0. Natural log of y is equal to 0. So how do we solve for y? I exponentiated. So we end up getting what? 1. So 1 is my answer on this one. So really, when we get an exponent, how do we bring him down? I natural log it. All right? And so then we get a natural log, and then we manipulate it to L'Hopital. All right? All right. So that's your homework. If you can evaluate with speeds, I would do it. All right, who's the slowest? Outside of constants, logs, then what? Pauli's, then exponential. We haven't gotten there yet. However, they will get there soon. Does anybody remember what the next one is? Factorials, and then x to the x into the ends.